Good morning and welcome back. This is awesome. We're now going to talk about one of my favorite topics, for sure, one of my roots into switching from condensed matter physics to studying things biological, and that really goes back to some super impressive work that was done in the laboratory of Carlos Bustamante. So, what I'm going to talk about here is where does this fit, first of all? We're now entering part of the course where I'm going to try to celebrate what my book co authors and I refer to as the secret of life in biology the secret of life is defiance. And when we say that, what we have in mind is this idea that there's a natural progression to things, to natural processes, in the absence of energy consumption. And what I mean by that is that systems will tend towards their state of maximum entropy. And this defiance notion is the idea that by investing energy, which often takes place through the consumption of ATP, but there's many other aspects to it that we'll get into, systems can actually contravene the second law of thermodynamics. And what we're going to see here is that this topic writ large is built around the notion in part of entropic elasticity, entropic springs, entropic forces. And that's a really beautiful idea. It's probably one of the most extraordinary things that I've learned in my journey through physics is this idea that the all important notion of entropy rears its head in such remarkable ways, and one of them is in the production of forces. And that's what we'll see here. So we're going to think about this classic experiment from the mid 1990s, in which what Bustamante and coworkers did was they attached beads to lambda phage DNA. So I remind you that lambda phage is a bacteriophage. That means it's a bacterial virus. This virus has a 48,500 base pair long genome. It's a workhorse of modern biology. And they took the DNA, and then what they did is they performed what I would think of as a classic mechanical test. When I was back in my days in condensed matter physics, thinking about the physics of materials, there's a machine known as an instron machine. And what these machines do is they load materials. You know, they're how you would measure the stress strain properties of aluminum or tungsten or silicon or whatever, which includes the yield stress in order to plastically deform the material and ultimately to fracture it. So the optical tweezers serves as a means for grabbing onto individual molecules and measuring their mechanical properties. And I think this really captured my imagination in a huge way. So as you can see in this paper, you know, DNA is unique among polymers, both for its size and for its long persistence length. I'll talk a little bit about persistence length at some point. But the idea is that one can pull on this thing, and as you can see here, what's shown in the graph is extension on the y-axis, and the extension is in microns units, and on the x-axis is force, and note the scale, which is femtonewtons, a very interesting scale when you think about 1,000 femtonewtons, which is the same as a piconewton, because you know we should remind ourselves that kBt is roughly 4 piconewton nanometers. The reason that's important, I think of this as being the natural energy unit of physical biology, because it demonstrates to us that the scales of molecular motors, where, you know, say a 5 piconewton force is exercised over distances of nanometers, is comparable to the magnitude of the force scale or the energy scale of thermal fluctuations. And so biological systems, at least the molecular part of the story, live at this in this netherland between thermal forces dominating on the one hand and deterministic forces dominating on the other. So our task is going to be to try to make a simple model of this kind of force extension property. What I will want to do in particular is I would like to calculate the fractional extension, and that's going to be some function of the force. So there's some nonlinear function of the force. Z is the extension, and L is the contour length of the polymer. And what we're after is to compute this constitutive law. This is amazing, because what I'm proposing is, not that I figured it out, but someone else did, was to use polymer physics to try to explain the force extension properties. Now, just as a little aside, you'll see here that there's a formula that they refer to here, and they are commenting here on the freely jointed chain model, and that's what we're going to work out. But there's a more sophisticated model, which is known as the worm-like chain model, which also accounts for elasticity. So we're going to think about this purely from an entropic point of view. And that's a good segue to this article by Tom Lubinsky. So let me just call this to your attention. I think it's very worth your while to read. It's quite old now. I mean, it's 25 years old, but it's a declaration. It's really a declaration of the existence of the field of soft condensed matter physics. And what Lubinsky shows here is all the interesting ways in which traditional hard materials, things like metal alloys, like semiconductor heterostructures, those things are awesome. There's no doubt about it. And it's really fun to work in the world of h bar not equals zero, where quantum effects matter. But there's this funny, interesting kind of materials where the dominant idea is that the objects of interest are collections of huge numbers of atoms, and often are in the form of macromolecules, whether we're talking about giant lipid molecules, or we're talking about polymers such as nucleic acids or proteins, whether we're talking about floppy membranes such as lipid bilayers, whether we're talking about colloids. That's the scale at which these things operate. And I just wanted to point out, the title of section 2, The Triumph of Entropy. That's really going to be one of the main motifs of this section of the course, which is the triumph of entropy. Okay, so, let's say 25 years ago, people were starting to be incredibly clever about finding ways to make molecular instron machines. So I mentioned already, these are, if you were to go into an engineering building like Firestone at Caltech, what you'd see is these machines. They're bigger than me. They grab onto a piece of steel and they actually load it. And here you see 4 different ways that people have found to apply mechanical loads to the macromolecules of the cell. In the upper left, this is a beautiful category of experiment that I first learned about at a conference in Germany, where I heard Julio Fernandez and Hermann Gaub, two great expositors for one thing, and great practitioners of this art of using the atomic force microscope. Dan Fletcher has done really interesting things using this methodology, where he has actin polymerizing beneath the cantilever. But the basic idea is the following: that you have a cantilever, you hold on to a material, and then you raise the cantilever, and just like me standing on a diving board, it will deflect. And using the theory of elasticity, one can relate the deflection to the force. It's a calibrated spring. Part B shows you the methodology that we're going to talk about here, which is the optical trap. The idea of that is awesome, beautiful, something we don't have time to go into. But, it's really this notion that light carries momentum. That's, the simplest thing for you to think about. And the bead actually causes refraction of light. And there's a momentum transfer. Because the photon's direction is changed, that actually produces a restoring force that tends to push the bead back to the focus. And so when the bead is pulled out of its focal point, we know the energetics of that. It's a quadratic well for sufficiently small displacements. And so it's a calibrated force measurement. Down here, this is a methodology that's been pioneered. So I should say, Bustamante, Steve Block, many other people have used these optical traps to great advantage, but I mentioned those two because their papers have been particularly inspiring to me. On the lower left, this is another amazing class of experiments, and I'm telling you because I remember 20 years ago, as I was first learning about these things, I was just blown away by the ingenuity of people. So the group that really caught my eye here is the group of David Ben-Simon and Vincent Croquet at the ENS in Paris. And this is a so-called magnetic trap, where they have a magnetic a magnet you see up there, the north and south poles, and they have a magnetic bead, and then by tuning the distance between the bead and the magnet, you can actually produce a force. The force has to do with the gradient in the magnetic field, and once again, it's a calibrated thing. One thing that's awesome about this is that the magnetic tweezers are very convenient for performing rotations, which you can see here. They've induced plectonemes coiling into the DNA, which is cool because then they can examine enzymes such as topoisomerase, which cuts and resolves such supercoiling. And the last one is an apparatus that was developed by many people, I'm sure, but the person that I used to talk to all the time that really caught my eye was Evan Evans, really a pioneer with this pipette aspiration stuff, which allowed him to measure the forces and the rupture forces in particular between receptors and ligands and so on. So at any rate, there's these different methodologies for performing single molecule biophysics, single molecule mechanical tests. And what we're going to do is we're going to try to actually compute the behavior of a polymer. So here, what I wanted to do was I wanted to introduce the toy model. So what we're going to do is we're going to do a toy model of a polymer. And we could do much more sophisticated things. And indeed, for the students in the course, you will do more sophisticated things. I'm going to do it in 1 dimension. You'll do it in 3 dimensions. It'll still be the freely jointed chain model. But if we were really pushing ourselves, we could include elasticity. That would be the worm-like chain model. That would require a lot more horsepower, but would still be super interesting. So the picture that I want you to have in mind is I'm going to imagine my polymer as being made up of a series of links of length A. And for my purposes, the polymer chain is going to be uniquely described. So the length of the chain is going to be number of right pointing links minus number of left pointing links times A. How does that work? So, you can see this guy is a right pointing one. This is right pointing. Wait, did I say that right? Yeah. Here's a left, and this is a left, and then this guy's a right, and then this guy's a left, a left, a left, a left, etc. So, so when I say NR is the number of right pointing segments, and N is the total number of segments in the chain. And what that implies is that NL is equal to N minus NR, and so I can substitute that in up here, and this gives me that another way of writing, and you'll see why this is convenient for me. Writing the length is 2 times the number of right pointing segments minus the total number, again multiplied by the segment length A. Okay, so so what we're going to try to do is, I want to find, the goal is we're going to use statistical mechanics and we'll do so to compute the average length. So when I write that symbol, stuff, that's defined as average of stuff. And just to give you a sense of how we're going to structure this, average length is going to be sum NR equals 0 to N, 2 times NR minus N, and then times P of NR. So what is this? So this is the probability of having NR out of N pointing to the right. I need an A in here also. This part right here, that part is telling us, well, the length of the guy with NR equals 0 or 1 or 2 or whatever is equal to that expression. In other words, this is the length, total length of polymer given NR pointing to the right. And our objective is to average over all the possible values of NR. So that's what this calculation really comes down to. Now, let me talk about how I'm going to think about this problem. So I very much like these sort of old school, sort of inspired by James Prescott Joule's experiment, representations of particular problems. And in fact, I'm going to cut this off here. We're only going to look at the right-hand side. So forget this part. So I'm going to hang a weight on the right-hand side of this polymer, and then what I'm going to do is I'm going to write down the states according to the statistical mechanical protocol. I'm going to write down the energy of those states. I'm going to write down the multiplicity of those states, again, in keeping with the statistical mechanics protocol, and then I'm going to write their statistical weight. Okay, so let's start at the beginning. So the first choice for a state would be NR equals 0. And that means all of them will be pointing to the left. So that's, here's the wall. That looks like this. ... So that's the state of interest. And what I'm going to do is I'm going to say my energy is equal to minus mg times L of NR, which in this case is minus mg, and then 2nr minus n times A, which in this case, just to keep going, is equal to mg capital N A. Note that the energy is positive. What I mean by that is, note where will I find that the energy is 0. I've chosen my energy 0, so comment. The energy 0 corresponds to NR equals N over 2. Note that if NR is equal to N over 2, then my energy up here, this thing, will be 0. That corresponds to half pointing right, half pointing left. Okay, how many ways can I have all of them pointing to the left? The answer to that is 1. So the multiplicity in this case is 1. And then finally, the statistical weight is multiplicity times e to the minus mgna divided by kBt. Okay, so we've done one of these. That's the first one. Next collection of states is NR equals 1. In this case, the energy is minus mg, and then 2 minus n times A. The multiplicity of this one is capital N, and so the probability, the statistical weight is e to the minus, and then mg, 2 minus n times A divided by kBt. Why is the multiplicity n? The multiplicity is n because I could choose any one of the total n monomers to be the one pointing to the right. Note, NR is 1. That means out of the total number of monomers, all of them are pointing left except for 1. And I have n choices as to where I put that. Okay, we're not going to look in general. We're going to look now at the case NR. For that case, we know that the energy is minus mg, 2nr, minus capital N times A. The multiplicity of this is given by the binomial coefficient. And hence, the statistical weight is that binomial coefficient times e to the, that should have been a plus up there, e to the mg 2nr minus n a divided by kBt. Let's talk for a moment about this binomial coefficient. So one way for you to think of this is that I have a capital N coin flips, and nr of them are heads, and n minus nr of them are tails, and the binomial coefficient tells us how many different ways we can distribute those heads and tail coin flips. And we already talked about this earlier in the context of diffusion. I'll go all the way now to the end where I have nr equals capital N. In this case, the energy is given by minus mgna. The multiplicity is 1, and the statistical weight for this one is mgna divided by kBt. Now, let's see if this jibes with our intuition. Note, let's consider the case where nr is 0 up here, and the case where nr is equal to n. The top one, this one, all of them are pointing to the left, and that's very unlikely. Notice it's got an e to the minus mg na over kBt. Contrast that with the one at the bottom, this one, where it's e to the plus mg na over kt. M is positive, g is positive, n is positive, a is positive, kBt is positive. So this thing has higher statistical weight than this thing. And that makes sense. Why does it make sense? It makes sense because this state is unlikely. The top state, this one, is unlikely because it requires us to lift the weight. This one allows the weight to drop. So those states don't have the same energy, and as a result, because of the Boltzmann distribution, they don't have the same probabilities. All right. So we basically have our states and weights. Now what we're ready to do is we're ready to try to evaluate, first of all, the partition function. So the partition function we see is nr equals 0 to n of n factorial, and then nr factorial, n minus nr factorial, and then e to the mg 2nr minus na divided by kBt. So that's our partition function. I can do a little bit of surgery on this by factoring out the e to the minus mgna divided by kBt. Bring that out in front. I'm left with a simpler expression. So I have my same binomial coefficient. And then I have e to the mg 2nr a divided by kBt. Great. Now, you might remember, so I'm asking you to recall, that x plus y to the n power can be written as little n equals 0 to capital N of n factorial over little n factorial, n minus little n factorial, x to the little n, y to the n minus little n. That's the binomial expansion. From that, I see that I can write this thing as, so I've got x equals e to the 2mga over kBt, and I've got y equal 1. So z, the partition function, is given by e to the minus mgna divided by kBt, and then 1 plus e to the 2mga over kBt raised to the n power. So that's awesome. We have a very simple result, and this simple result gives us everything we need in order to compute the length. All right, so now we're ready to compute the average length. The average length, as I already said earlier, is going to be given by 1 over z, and then times nr equals 0 to capital N of 2nr minus capital N times a, and then times the binomial coefficient piece, nr factorial, n minus nr factorial downstairs, and then times e to the I'm just going to copy this and bring it down. Copy. I should write it out. Okay, I blew that. Sorry. So this is 2nr minus capital N A mg divided by kbt. So that's the average length. Why is that true? Because the way to think of it is that this piece is the probability of nr, and this piece right here is L of nr. So what I'm doing, by the way, I was a little bit sloppy because P of nr also includes the 1 over z. So those two pieces together give me P of nr. And so I've got this very nice expression for the average length. So now we just need to keep our nerve and keep on trucking. So this can be written as a sum of two different terms. So I've got 2a over z, and then nr equals 0 to capital N, nr, and then n factorial over nr factorial, n minus nr factorial, and I think I should have factored out already something, so let me do that. I have an e to the minus n a mg divided by kbt. So that was factoring out this piece right here. And then over here, I'm left with e to the 2nr mga divided by kbt. So that's the first term. And then I also have a minus na over z, e to the minus n amg divided by kbt, and then sum nr equals 0 to n of n factorial over nr factorial, n minus nr factorial, and then e to the 2nr mga divided by kbt. Okay, I'm gonna refer to this first sum as term 1, and the second one as sum 2. So what we need to do now is we need to do our homework. We need to go do the calculations. And the main trickery is, so I'm going to write down number 1. Let's copy that and bring it down. Okay, so what do I notice about this? It looks a little bit painful, but this is an opportunity for me to introduce one of my favorite tricks. So notice that this whole thing I could rewrite as d by d mu of nr equals 0 to n of n factorial over nr factorial n minus nr factorial e to the mu nr. Why is that? Notice what happens when I take the mu derivative. When I take the mu derivative, what it does is it grabs this nr and brings it down stairs. In other words, d by d mu of e to the mu nr is equal to nr e to the mu nr. So that's super convenient, because what it allows us to do is to replace the original sum, which features this annoying nr right here, with a sum that we know how to do, because this is nothing more than the usual binomial sum. So let's write that out. So this thing becomes d by d mu of nr equals 0 to capital N, and then n factorial over nr factorial, n minus nr factorial, e to the mu nr, which is equal to, this whole thing is equal to 1 plus e to the mu to the n power. So when I take the mu derivative, what I'm left with is n, 1 plus e to the mu, n minus 1, times e to the mu, which now we can rewrite as n 1 plus e to the 2mga over kbt times e to the 2mga divided by kbt. And that's all to the n minus 1 power. Okay, notice that there is a 1 over z sitting out in front here. And what I want you to notice is that so now if I, putting it all together, I guess I would say, so term 1 ends up being equal to 2na e to the 2mga over kbt over 1 plus e to the 2mga divided by kbt. How did I get that? Because notice that z has, let's go up here, yeah, z has a big N. Oops. There's an exponent n, and when we did this assessment of our derivative, we got an n minus 1. That means we're left with the 1 over 1 plus e to the 2mga divided by kbt. Okay, what about term 2? So term 2, this one's more straightforward. I will copy it and bring it down. So this term, I can already recognize that this whole thing is going to be 1 plus e to the 2mga divided by kbt to the n power. And so when all the dust settles, what I'm left with is minus na. That's it for that term. And so now we have our result. Average L is equal to 2na e to the 2mga divided by kbt over 1 plus e to the 2mga over kbt minus na, which we can simplify further. So first, I guess I'm going to write this as average L divided by na. So that's a strain. I've divided through by na, which is the contour length. NA, you can see, is the contour length. It's the total length of the chain when we stretch it out. And what I find is that I get e to the 2 mga kbt minus 1 over e to the 2 mga kbt plus 1. And I can simplify that using my favorite, or one of my two favorite things, which is I like to add 0 and I like to multiply by 1. So here I'm going to multiply by e to the minus mga kbt, e to the minus mga over kbt, and this leaves me with e to the mga over kbt minus e to the minus mga over kbt divided by e to the mga over kbt minus plus e to the minus mga over kbt, which I'm going to finally write as e to the fa over kbt minus e to the minus fa over kbt divided by e to the fa over kbt plus e to the minus fa over kbt, and finally that's equal to the hyperbolic tangent of fa divided by kbt. Here we used f equals mg. Why? What was that all about? As I said, I like this idea of being concrete about the loading device. So notice here, these weights that I drew, that's not the way that the experiment's done. You don't hang weights on a piece of DNA, but we can think effectively of the optical trap as a weight. So it was convenient for the purposes of this little fiction to pretend that we had hung a weight. We did that, and when all the dust settled, we got this very, very beautiful expression. So note that what we're claiming is that strain Z over NA is given by this relationship between force and displacement. I have an interlude on Taylor series, which I want you to watch, but for my purposes here, I want to just make an observation. Note, for FA over KBT much, much less than 1, then I can replace Z over NA. That's going to be approximately equal to 1 plus FA over KBT minus 1 minus, it's going to be 1 plus, no, 1 minus FA over KBT, and then the denominator is 1 plus FA over KBT, and then plus 1 minus FA over KBT, which leaves us with FA over KBT, or that F is equal to KBT over A times Z over NA. So this is Hooke's law. So what we find is that for small loads, there's a linear relationship between the force and the displacement. But note something very interesting, which is that the spring constant, which is this prefactor KBT over A, note that the spring constant is going to increase with temperature. It's really the opposite of what you'd find in aluminum. So what have we done? I mean, what we've done is shown here. So I did this model, this one. And in the homework, some of you will do, like these models, these other two. The off-lattice one is very amusing. What we're plotting on the x-axis is the dimensionless force. What we're plotting on the y-axis is the fractional extension. Note, the largest that z could be is, actually, I think maybe I messed up my notation. So I was calling this average L. So let me repair that. Sorry. Yeah, so average L, and that's what I was calling Z, so that's the strain. But what you see in this graph is that when you have a huge force, the chain is fully stretched out, as you see here. And at that point, the average length is equal to the contour length, so it's 1. Z over NA, or sorry, average L over NA should be 1. And that's indeed what we find, this saturation. In the small load limit, we knew that this thing was linear, and that's what I plot here. So it's a straight line, that's Hooke's law. So this is the Hooke's law regime over here. This is the saturation regime out here. What actually would happen in the large force limit is you'd start to stretch the bonds, and this thing would go up, actually. So I think this is the essences of what I wanted to say. So what have we accomplished? So I just want to remind you, there's this classic experiment done by Bustamante and company, and note that they're plotting on a semi-log, and so I can't make an exact comparison between what we just calculated in this graph, but they're plotting on a semi-log. They measure the force extension properties. I wanted to note that there's this beautiful field of single molecule biophysics which allows us to impose loads on lipid bilayer membranes, on polymers, on proteins, whatever. And I also just called attention to the triumph of entropy. So we got very concrete. We said, let's look at a toy model of a one-dimensional polymer chain, and let's examine its mechanics. And it's audacious to imagine that we can compute the mechanical equation of state from first principles, from statistical mechanics. I mean, we basically did a statistical mechanics calculation, and the outcome of that was a force extension curve, a nonlinear force extension curve to boot. It's not just simplest Hooke's law. So what did we do? We wrote down the states and weights. We followed the statistical mechanics protocol. We identified our states using the parameter NR. NR is how many of the monomers are pointing to the right, and that can run anywhere between 0 and capital N. The multiplicities have to do with the number of ways of generating a particular number of heads and tails, and then the statistical weight is the combination of e to the minus energy and this multiplicity. That allowed us to get the partition function, from which we were able to compute the average length, and we got this very, very simple, sweet formula, which I show you right here. So that's really our principal result, is this formula, which is really beautiful, I think. And as I said, this to me, in the early days of my own adventures in my incomplete and imperfect education in biophysics, was to be blown away by what people were able to accomplish. And then we made a little bit of a move to make an approximation, which is in the small force limit. We showed that this yields a Hooke's law, but note that the intuition for this Hooke's law is really different from the ordinary Hooke's law that you're used to, because of this really interesting temperature dependence. What's the meaning of that? The meaning is that as I raise the temperature, the anger of the entropy increases. The entropy is more and more offended by the fact that when we pull on the chain, we're pulling out the entropy. We're pulling the wrinkles out of the chain, and those wrinkles represent the entropy. And so we are increasing the entropy. We have to do work. And I told you earlier, if the polymer is left to its own devices, it will go to its maximum entropy state, which is closed up. And in fact, we know what it's going to be for this one-dimensional chain, which is NR equals N over 2. It's going to be folded up on itself so that half are pointing to the right and half are pointing to the left. That is the maximum entropy state. So in order to get it out of that maximum entropy state, we have to do some work. And that's a metaphor for what happens in all sorts of senses in biology, which is to get the system away from its maximum entropy state, some cost has to be paid, and here it was the cost paid by the loading device.